My name is Erik. I'm the Executive Director of the Takshnak Watershed Council, and this is the third in our series of environmental science lecture Zoom topics by Erik Stevens entitled Microclimates of Haines, Simplicity and Complexity. All videos will be available on the Takshnak website, which is takshnak.org. And next week's Zoom talk will be about hooligan history, local subsistence history, and cultural significance. And we'll also talk a bit about the research that the Takshnak Watershed Council has been doing with the Chilkoot Indian Association for quite a number of years now on our local hooligan population. So without further ado, I'd like to introduce Erik Stevens, our speaker tonight. Erik has a master's degree in remote sensing, earth and space sciences from the University of Colorado Boulder, with a certificate in atmospheric and oceanic sciences and a certificate in oceanography. Previously, he worked for the National Center for Atmospheric Research on an airborne dual Doppler study of the rapid intensification of hurricanes. He studied turbulent ocean processes for the Cooperative Institute for Research in Environmental Science and worked on an experimental Mars rover project at NASA's Jet Propulsion Laboratory. He holds a Level 3 certification from the American Avalanche Institute and is a professional member of the American Avalanche Association. He has been a ski guide for Alaska Mountain Guides and a forecaster with 11 seasons of experience in Haines. Thanks, Erik, for putting this together for us.
Yeah, thank you, Derek, and thanks Takshnak for holding this really awesome series of lectures. I really enjoyed Cindy's, and I hope all of you out there today, and hopefully some of you watching the recording at some point in the future, find this to be really helpful. So thanks for joining us. I'm going to talk about our Haines microclimates, and I originally thought I would title this talk Simplicity and Complexity, and I think I'm still going with that. But as I put the presentation together over the last several weeks, part of the idea was for me to force me to bring my thoughts on microclimates together into a hopefully coherent picture. And I'm not sure how coherent it is, but I'm going to try my best. It's definitely a difficult topic. And yeah, here we go. Let's give it a shot. Okay, so first of all, just basic definition of microclimates. We're all on the same page here. A microclimate is a local set of atmospheric conditions that differs from those in the surrounding areas. And the term could refer to areas that are really small, like a garden bed or a cave, or areas that are really large. And I pulled up this map of the big island of Hawaii down here, because Hawaii is actually a really interesting example of microclimates. And at this point in the presentation, I'll just say that when I say the word microclimate, what I'm talking about is not really the size of your garden bed or your driveway, but more a microclimate the size of these small pockets that exist. So, something a couple miles across. And we have a lot of those microclimates here in Haines, as a lot of you have probably experienced. And we'll come back to Hawaii later. So let me see if I can move this thing that's in the way of my presentation. 1 second here. Zoom bar. How does weather forecasting, the question is, does weather forecasting work in Haines? And I hear all the time from people that, what's the point of even checking the weather? It's always wrong. I'm just going to be prepared for anything that may come, and hopefully it all works out. So people often are thinking, why is the forecast always wrong? Well, the truth is it's not always wrong, but it does seem like it sometimes. And our human nature is to remember the times of the forecast that it was wrong, and not really remember the times that the forecasters got it right. Because a lot of the time we're out playing in the sun, or we're sitting at our desk at work or whatever, and the forecast was right and we didn't really pay attention to it. Another reason the forecast can be wrong sometimes is because a lot of us are getting our forecasts from the wrong source or from a bad source. And I'll talk more about that. we often misinterpret the forecast, even if we get it from a good source. Either it's easy to misinterpret what the forecast is saying, or another way to put that is that the forecast is bad at communicating what it really means to tell you. And that's something that the National Weather Service has spent a lot of time working on, trying to get the communication right. But it's difficult. And the reality is this stuff is complex. The communication is complex. The forecasting is complex. The physics are kind of complex. They're not terribly complex. So how do we get a good forecast then? And I said some of us get our forecasts from a bad source. Well, there's really only one good source for weather forecasts in our country, and in Alaska especially. You want to always get your weather forecast from weather.gov. That's the National Weather Service, and there's a Weather Service office in Juneau. So they're pretty close to local forecasters. Since they're in Juneau, they're not here, and sometimes they're a little bit out of touch with Haines, but they do a pretty good job, and they work really hard, and they definitely know what they're doing. A little bit more locally, there's the Haines Avalanche Center website, which is at alaskasnow.org, and you can click on Haines. So we provide an avalanche forecast for Haines in the winter months, and that avalanche forecast is going to include a little bit of a weather forecast in it. Unfortunately, we don't really have time to provide a whole weather forecast, so it's not as comprehensive as what you're going to get from the Weather Service at weather.gov. But beyond that, when you're getting your forecasts from the National Weather Service, you still can improve what the information that you're gathering if you have some capacity to be your own local forecaster. And basically what I mean by that is to understand our microclimates and understand what they mean when they say chance of rain, chance of snow, northwest wind, southeast wind, et cetera, et cetera. So that's kind of what we'll go into tonight, understanding our microclimates. And I can already hear, some of my ski buddies and adventure partners out there saying, but it's too complex, this is way too much work, and it's all too unpredictable here in Alaska. Our weather is so crazy. And they are right to an extent, especially at small scales and very specific locations. One specific mountain could have very different weather than the mountain right next to it. And that's true. But on the large scale across the whole borough or across the northern panhandle, for example, the forecasters get it right a lot of the time. They're actually really good on larger scales. And that's because they're interpreting the data that comes out of weather models. And the weather models are really good at short-term 1 or 2 or 3 day forecasts on a large-scale region. And then it's up to the forecaster to interpret that large-scale forecast and bring it down to a smaller scale, like City of Haines or Haines Customs. And then I kind of already mentioned this, the other complaint, there's too many microclimates. How can the forecast ever be accurate? Well, there are many microclimates, but this is really important. In my opinion, they are predictable microclimates here in Haines. And so I'm going to present to you my model or my theory of how the microclimates work here. And hopefully it's mostly correct. So here's our plan for the talk tonight. I'm going to try to start with simplicity, and then we're going to work our way into more and more complexity. And hopefully by the end, you guys won't have too much information overload. But we'll start with just basic meteorology, because we need to lay down a little bit of groundwork before we go into the details. Then part 2 will be just some examples of how some of our particular weather events have set up over the region. So I'm going to go through, I think, 4 different storms and just show you what they look like and what the winds were doing, and then what the resulting precipitation was. And then part 3, if you guys can stick around throughout the whole talk, it's worth it, because part 3 is where we really get into the meat of the situation, and that's the terrain in our area and how that affects and how that creates microclimates and where microclimates are. So I'm going to try not to take too long here, but it is a lot to talk about. So, introduction to local weather patterns. The first thing I'm going to mention is that when I talk about the winds, The winds, there's two different things that I'm going to talk about. There's the wind speed and wind direction at the surface. That means at ground level, like on the fjord or in the valley, versus the winds that are blowing at 850 millibars. And what that means, if you look at this image, picture this as a column of the atmosphere going from the surface of the Earth up into the top of the atmosphere. And this is the pressure level on the right here. So 1,000 millibars is basically the pressure at the surface of the Earth. And as you go up in altitude, the pressure decreases. So the 850 millibar level is roughly, in Haines, it's somewhere around 4,300 feet, which is about mountaintop level. And in the summer, it's a little higher, and in the coldest times of winter, it can be a little lower. It moves around a little bit. But roughly speaking, this 850 millibar level winds, those are the winds blowing at mountaintop level, as compared to the winds that might be blowing at the Earth's surface. So, to complete the diagram here, I've drawn some mountains, and then the winds at the top of the mountains and above the mountains are not affected by the mountains so much, and they kind of blow however they want to blow. We call that a geostrophic wind or a synoptic scale wind. But the winds at the surface in the fjord could be blowing a totally different direction. And in fact, they're usually blowing perpendicular to each other. So just keep that in mind when I talk about the winds. And if I mention 850 millibar level, basically what that means is mountaintop level. Also, for the rest of the talk, I'm only going to talk about precipitation. I'm not going to talk about temperature microclimates or wind microclimates because while they totally exist, they're not as high of an impact, and it's just too much to go into. Precipitation is the main impact. Basic meteorology, how does precipitation form? What do we need to make rain or to make snow? Well, we need to have moisture, and moisture levels vary throughout the atmosphere. But pretty much a good bet that anytime the wind is blowing off the ocean, here in Haines, we have plenty of moisture. And anytime the wind is blowing off the continent, like out of the Yukon or British Columbia, we don't have enough moisture at all. And usually it's very clear during those time periods. It's not many clouds. So you need to have moisture. Then you need to have lift, because you have to lift that moisture up into higher, cooler levels of the atmosphere where that moisture can condense into clouds and then eventually rain. And there's four main types of lift. There's frontal lift, which means cold fronts or warm fronts, or a really important phenomenon called overrunning, which I'm going to talk about a lot and is very important here. Happened a lot today, as a matter of fact. Then there's dynamical lift, which is a large scale, it's on the scale of a low pressure system, a couple hundred miles across, for example, or convergence, which I will talk about as well. And then there's probably the most important one, which is orographic lift. Here in Haines, very, very important, and it causes most of our microclimates, and that's terrain-induced lift. Then it's going to create your rain shadows, your wet side of the mountain versus your cold or your dry side of the mountain. And then there's convection, which I'm not going to talk about because it's relatively minimal effect here. And the other thing you need, the third ingredient for precipitation, you need a condensation nucleus, which I'm not really going to talk about tonight either because there's usually enough of them here. There's little particles of salt in the air, there's smoke, dust from Asia, ice crystals. You basically just need anything that the moisture can condense onto, and that is usually present here. So yeah, just keep in mind that there's a lot more going on than I'm going to be able to talk about tonight, but I'm going to focus on overrunning and orographics. So first of all, frontal lift or overrunning. Here's a great picture of what that looks like. I think this is from Encyclopedia Britannica. I used to have a credit on here. I don't know where it went. So if you picture there's a bunch of cold, dense air sitting on the ground, which we usually have in the winter up here. That cold air is very dense. It's very stubborn. It doesn't want to move. It doesn't want to go anywhere. And if you have warm south winds blowing up, from the south trying to push that cold air out of the way, well, the cold air is very slow and stubborn and dense. It doesn't want to go. So what ends up happening is that warm air, which is less, let me go back up. That warm air rides up over the top of the cold air. And I'll refer to this as a cold air dome when I'm talking about the Chilkat Valley or the fjord, because we often have a cold air dome sitting in the valley. And when a storm comes in like it did today, and it tries to bring warm tropical air up from the south, that warm air ends up overrunning the top. And that overrunning creates lift. And at the steepest part of the lift, the steepest part of this angle here is where the heaviest precipitation is going to fall. So it tends to be really heavy right where the tongue of cold air is at its steepest, at the front of the cold air. Yeah. So today, for example, this is a weather map of the weather stations today. So here's Haines, and these wind barbs are showing the direction of the wind and the strength of the wind. So you can see, well, first I'll talk about temperatures. This number here on the left side of each barb is the air temperature in Fahrenheit. So today in the middle of the day, it was 19 degrees at the airport, 26 in town, 23 up at Skagway, 20 up the highway, and it was 30 down at Eldred Rock. And you can see there's a south wind, a pretty strong south wind blowing at 32 miles an hour up the Lynn Canal. There was earlier today anyway. And so this is a good example of an overrunning situation. This is a setup where we get overrunning. You have a dome of cold air that's trapped in these valleys in the upper Lynn Canal. And then you have a stream of warm air trying to blow northward. And it's trying to push that cold air out of the way, but the cold air is really dense and it's stuck in these valleys. So the warm air rides up over the top and you get an overrunning event right where the cold air at the tongue of cold air is sitting. So that was one thing that was happening today. Another really important kind of lift, convergence. So think about if we were in the fjord here and there's a south wind coming up from this direction, and then on the other end of the fjord you have a north wind blowing. Where those two winds meet in the middle, it's got nowhere to go but straight up. And that creates very strong lift in a very localized area. So you get heavy precipitation with convergence there. And going back to this diagram from today, we had that exact same thing also happening over Haines today. We had a south wind blowing up the fjord. We had north winds coming down from Skagway, north winds coming down the Chilkat Valley, and this is at the surface here I'm talking about. And so where the south wind is meeting the north wind, somewhere in this region, you have a very heavy band of precipitation, and that's convergence flow. And convergence and overrunning sometimes happen in the same spot in the fjord, and sometimes you'll have one but not the other. But often it's both working together, which we definitely had today. Oh yeah, so there's some arrows of those converging winds all converging in one spot right over Haines. And I'll refer to that as a convergent zone, where there's either overrunning or convergent wind happening. So here's a picture of what that looks like looking down the fjord. This was last year in January at one point, but we had a north wind blowing down the fjord. Here's Fort Seward right here in the boat harbor. And if you look down here in the distance, down near Seduction Point and Glacier Point, that area, you can see a really thick wall of precipitation, and that was a very heavy snow shower that was just stuck there, persistent heavy snow shower. It was probably snowing 2 or 3 inches an hour, just very, very heavy snow. And that's right where that north wind is blowing south, and it's converging with a warm south wind that's coming up the fjord. So that's convergence. Then there's orographic lift. So orographic lift, I think a lot of people are familiar with this. When the wind is blowing at, let's say, 850 millibars, when the wind is blowing from left to right in this diagram, and it's trying to push the wind up the mountain slope, that's going to cause a lot of lift as the air blows up the mountain. And you get a lot of precipitation on this windward side of the mountain here. And then by the time it gets to the top, it's lost a lot of moisture and it starts descending down the backside. And so it's drier already. It starts warming up as it descends, and you get a very warm, dry area on the right side of the diagram here on the leeward side of the mountain. So this is your typical rain shadow effect, which we have a lot of in the Chilkat Valley. And of course, you know, the Glacier Bay side of the mountains gets much heavier precipitation, a lot more snow and a lot more rain. So that's orographic lift. And this is the simple version. But, oh yeah, before I have a couple pictures before I go to the detailed version. So here's a photo of some orographic lift happening over the Chilkoot Range across the fjord from Seduction Point. You can see the wind is trying to blow up and over the mountains, and it kind of hugs the surface of the mountains and descends down the other side. Here's another photo of that. This is over by Taisanka Harbor. So you can see the winds are creating these clouds as they lift up over the mountaintop, and then they come back down the other side. That's orographic lift. Okay, so here's the more complex view of orographic lift. So we have our rising air and our falling air, but there's a lot more going on than that, right? Because really you can think of the atmosphere as being a river, and we are at the bottom of the river, and the flow is flowing across these terrain features. And just like you would have a rock in a river, and the water tends to flow down behind the rock and create a big jump on the other side, if anyone's a kayaker or a rafter, you'll be familiar with the term of a hydraulic. Well, these are hydraulic jumps, and it's a phenomenon of fluid dynamics that is pretty complex. And it depends on how fast the flow is moving across the mountain range. It depends on how high the mountain range is. It depends on the buoyancy and the stability of the air and the temperature of the air. But I just wanted to mention that there are these complex dynamics that happen in the lee side of a mountain range. Sometimes you have hydraulic jumps, you get these wave clouds that happen. If anyone's been to the Front Range of Colorado, you see these wave clouds all the time. Lenticular clouds are a good example of that. And we'll come back to that as well. Okay, now let's take a little trip to Hawaii. And I put this diagram in here as a demonstration of orographics because orographic lift can be complicated when you have really complicated terrain. But these Hawaiian islands, some of them anyway, like if we look at Kauai here, that's a very simple piece of terrain. It's a single mountain, and it's pretty much open ocean on all sides around it. And the trade winds blow out of the northeast pretty consistently, not all the time, but a lot of the time the trade winds are blowing out of the northeast in Hawaii, and they come across a mountain like Kauai, and they form this really kind of uniform precipitation pattern. And this is a really typical pattern for an orographic uplift. And then the rain shadow in the lee of the mountain. So that's the simple case. But if you were to look at a more complex piece of terrain, like the Big Island here, which has 1, 2, 3, 4 main summits, and they're all at different elevations, and some of them are very high, you can see the pattern's not so simple. You have this heavy rainfall on the northeastern side, and you have a rain shadow on the western side, but then you look at what's going on down here near Kona, and this doesn't really fit that model. It's not that simple. You would expect this Kona rain belt to be in a rain shadow, and it should be drier here, but it's not. And this is actually apparently the reason that Kona coffee is able to grow. And apparently it's one of the only places in Hawaii you can grow coffee. It has this very particular microclimate called the Kona rain belt. And from what I gather, I'm not an expert in Hawaii, but from what I gather, the reason that's there, that complicated microclimate, is because the typical trade wind flow that comes around the mountain actually wraps around the lee side here, and you get a bit of upslope winds. And that doesn't always happen, but it happens some of the time when the flow conditions are right and the sun is shining just right. You can get the flow to wrap around the island and cause uplift and a rain belt in this leeward, typical leeward area. So Hawaii is a cool example because it shows both the simplicity of orographics and the complexity. Okay, so that's the intro meteorology lesson. Let's start talking about some particular storms here in Haines. This is part 2. Yeah, examples, set up for particular storms. So I'm going to talk about 5 particular storms for this event, or for this section of the presentation. And the main thing I'm going to talk about is the flow direction. And I'm talking about 850 millibars especially, because that's going to be really important. So we'll look at 2 really snowy months, November 2011 and January 2012. Those were basically the record snowiest months that we've had in Haines, and also the snowiest year we had in Haines. And then we'll look at especially rainy events, and I'll explain why I'm breaking these up into separate events later. So 2015, this was a midwinter thaw event that I don't know if anyone remembers. There was a cold, snowy winter, and then it just started pouring rain, and it was like 49 degrees in the middle of January. It was a very strange thaw. And then I'll go into our atmospheric river events that we had this year. and then the comparable atmospheric river from 2005. So there's going to be a lot of data coming up, and I apologize for that, but bear with me. This is the November 2011 snowpocalypse, where we had 126 inches of snow that month, which was the record snowiest month in Haines. Most of that snow fell during, I think I have some circles, here we go. Most of that snow fell during a 1 week period, and it was culminated by this very heavy overnight snowfall of 21 inches, which I remember very well because I had to shovel it the next day. And yeah, we built up a lot of snow depth very quickly that month. And this was because of a very persistent weather pattern that I will pull up on the Climate Reanalyzer, which is a really neat tool. Here we go. So here we are looking at, November 2011. And if we look at, so here's Southeast Alaska right here. Hopefully you guys can see this on your Zoom screen. I've tried my best to make things readable, but we'll have to, hopefully you can see it. What we have is low pressure in the Gulf of Alaska, like we typically do during a snowy event. And what that means is that the flow at 850 millibars is flowing parallel to these lines, and it circles around a low, and it's coming up from the south or just a little bit east of south. What I'm going to call it south-southeast flow. Here in Haines, you can see these lines are coming up out of the south-southeast across our fjord. And let me animate this a little bit. So to show several days in a row here in November of 2011, the reason we got so much snow is because we had a very persistent weather pattern. That low pressure, this is 1 day at a time that we're going through. So several days in a row, we had these low pressures that were just stuck and persistent south-southeasterly flow. And it just kept dumping snow day after day. So that was November 2011 and south-southeast flow. Now let's look at January 2012. Very similar setup, very similar situation. We had 1 week of very heavy snow in the beginning of the month, another week of very heavy snow at the end, and this culminated in, there's 26 inches plus another 6, that was 32 inches in 3 days right there. Snow depth was 72 inches on the ground. It was very, very snowy in January of 2012. And if we look at what that looked like, so here is January 2012. And once again, it should look familiar. It's the exact same weather pattern. Because it turns out that our really snowy events tend to be from the exact same weather pattern, and our really rainy events also tend to be from the same weather pattern. We have very persistent weather patterns here. They're different between the two different types of event, but they're persistent. That south-southeast flow leading to snow. Oops. Where is my presentation? There we go. So that was a snowy type of event. Now let's look at the wet, warm, rainy type of event. Here's January 2015. We had very warm weather. It's 46 degrees in the middle of January, a low temperature of 42. It was just balmy. And it rained very hard. There's 2.3 inches of rain one day, 2.6 inches the next day. A lot of rain that week, very warm. And that storm looks like this. It's very different by comparison. You have, oh no, I stopped my screen share. Let's go back to that. Here we go. You have strong southwest flow coming off the ocean, southwest river of flow, and that's basically an atmospheric river aimed right at the panhandle, and that flow goes out of the southwest across our fjord. So those are our really warm, rainy events. Very different than the snowy events. And now, just for completeness, let's look at some actual atmospheric rivers. So here's November 2005, which was another really significant event. Um, we had very heavy rain during that period. A lot of people remember Mud Bay Road washed out really bad. And up until this last year, this was the biggest rain event we had on record in Haines. But the December 2020 event really kind of blew it out of the water in a lot of ways. And one of the differences, while I'm here, I'll mention that there was very little, almost no snow on the ground leading up to this November event. Whereas with the December 2020 atmospheric river, we had a lot of snow on the ground, and there was a lot of snow melt that happened in addition to the rain. So that really increased the severity of it. But regardless, November 2005, if you look at the weather pattern on that date of that main event, it was almost identical to the other warm, wet rain event where you have strong southwest flow, low pressure to the north, high pressure to the south. Very familiar, right? And here's December 2020. Like I said, we had 24 inches of snow on the ground, and that was a very dense, very moist 24 inches of snow with a lot of water that needed to melt out. And even with that snow on the ground, then we had extremely, extremely heavy precipitation over a 2-day period, and warm weather as well that melted most of that snow down. And what the December 2020 event looked like was very, very similar, a little bit stronger in terms of the flow here. There's a lot, these lines are packed closer together, which means stronger winds. But they're still coming out of the subtropics. They're still blowing out of the southwest and aimed at the panhandle here. And they might have been coming a little bit more out of the south, but it's still generally a southwesterly flow during our December 2020 rain event. And to compare, this is another view of the atmospheric rivers. So this chart is actually showing, these black lines are showing the pressure. So the winds are blowing along these lines, just like in the previous charts. But the colors here are showing precipitable water, which basically means it's the total amount of moisture throughout the column of the atmosphere. And this is how you know an atmospheric river is really happening, because you see these really high values of PW, or precipitable water. And during our December 2020 event, you had very high levels of water in the full column of the atmosphere, and it was aimed just directly right at the upper panhandle. Couldn't have been more direct of a bullseye. And during that week, this river fluctuated south and north a couple of times, but generally stayed right over us. And if we look at November 2005, by comparison, our other big atmospheric river event, you can see it's a very similar pattern. You still have low pressure to the north and high pressure to the south, and you have these tight ISO lines where you have relatively strong winds blowing across the panhandle from the southwest, and the atmospheric river aimed right at us. But it's a little bit less intense, not as large of an atmospheric river, not quite as much moisture, and not quite as much wind. Yeah, the December 2020 event was pretty spectacular. So, which leads me into part 3 here, and this is where we're going to really get into the weeds of it, and it really gets complex, because we've talked about southwest flow, and we talked about southeast flow a little bit, and hopefully by now you know what I mean when I say southwest flow. I mean the flow at 850 millibar level, as shown in those other maps. But if we just look at a satellite image of the northern Lynn Canal area, here's Lynn Canal right here, that little thing is Haines Airport. And here's Chilkat Valley going up to the Haines Pass. And this view is a good way to show where the mountains are really tall and where the precipitation is hitting and where it's stopping. Because you have glaciers, anywhere you have tall mountains, you have glaciers, but you also have these mountains acting like a fence. That fence is in the upper, the Chilkat Valley area. And even though there's tall mountains up here in Canada, they're not nearly as glaciated. And one of the main reasons is because as the moisture comes in from the south or the southwest, it basically gets trapped by these mountains, and it deposits all this snow in Glacier Bay and the Fairweather Range, and not as much moisture makes it inland. And the same thing happens when the wind's coming out of the east. We have another huge fence to our east that prevents anything from getting over the fjord, or over the mountains into the fjord. And really, if you look at this, the only way for a strong storm to really pump moisture directly into the Haines area is if the flow is coming right up along Lynn Canal and aimed directly up Lynn Canal. That's the only real break in the mountains, the only significant break in the mountains. So keep that in mind. Oh, there's one more break in the mountains I want to point out. This right here is the Endicott River, which goes through the Endicott Gap. And it turns out it's a pretty significant break in the mountains. And I think it plays a pretty important role in why Mud Bay and the Chilkat Peninsula is so wet. So here we go. So I'm going to talk about two main different flow regimes. Southwest flow, which is our warm, wet storms with heavy rain in our atmospheric rivers. So here's a southwest flow situation. We have the winds blowing at 850 millibars out of the southwest across the Chilkat Range and the Takensa Mountains. And they're going to be driving strong surface south winds through the fjord. So Eldred Rock usually blows 50, 60, 70 miles an hour out of the south in this kind of a situation. And that wind makes it up the Chilkat Valley, and it goes all the way up through the pass, and the south winds haul through the pass, and they haul through Skagway as well. So if we think about how the flow is moving over these mountain ranges, and we think about orographics, and we think back to those maps of Hawaii, for example, well, we can come up with a theory as to where it should be wet and where it should be dry. And my best take on that, based on the terrain and the direction of the flow from the southwest specifically, I think we really should have a lot of rain shadowing in the Chilkat Valley. And one of the things I've gathered is that it's quite a bit wetter from Mud Bay south, especially, in the fjord. And if it kind of makes sense because there is this gap in the mountains with the Endicott Gap. And I think that does allow moisture to wrap around the mountains and make it into just this part of the fjord, but definitely not all the way up to Haines. We have strong downsloping over the town side of Haines. And you can see that a lot of the time when the wind's blowing hard out of the south, which means we have a strong southwest flow, you'll see a sucker hole open up in the sky right over Haines, right over the airport. You'll have this beautiful break in the clouds and some blue sky, and the sun will shine through. And it may only last for a couple of minutes, but the reason that sucker hole exists is because of downsloping coming off of the Takensas and the Chilkat Range. So there's my theory for southwest flow. But there's one more thing that happens here. Let's see. There we go. With southwest flow in the winter, I've noticed that we get convergent zones, and they tend to happen up the highway up near 33 Mile or the border, Rainy Hollow. They can get a lot of snow sometimes during these southwest flow events. And I believe that happens because the cold air that's trapped in the valley, it takes a lot longer to scour out all the way up here, and it's surrounded by tall mountains. So that cold air acts as a cold air dome, and these south winds ride up over the cold air, and you get overrunning, and you get convergence when you have north winds coming down and meeting the south winds. So with these southwest flow events, we sometimes will have heavy snow events up near the border. And I've also noticed another convergence zone up near Nottahini, which I'll probably move on and not talk about, but it's an interesting one that I have no data to prove, but I think is there. So now let's talk about southeast flow, which is this other major flow regime that I'll focus on. And this is a storm like what we had today, where you have the flow at 850 millibars is wrapping around. There's usually a low pressure out here in the Gulf to our west or our southwest, and it's wrapping the flow around it. And it happens to line up pretty closely with the fjord and then make a left turn and move towards the west. So the flow is following these big arrows at 850 millibars. And that's driving north winds in the fjord. So we'll have a cold Arctic north wind coming out of Skagway and a cold north wind coming down the Chilkat Valley. And that's at the surface. And based on this flow pattern, we'd expect downsloping in the Chilkat Valley, downsloping up near the pass, and dry conditions in Skagway because of the mountains blocking the flow there. But we would expect a lot of precipitation to fall near Mud Bay and the Chilkat Peninsula because the flow is just being directed straight up the fjord, and there's really nothing blocking it when you're out there exposed in the fjord. But one of the things that this also leads to, when you have the cold air coming down from Skagway, cold air coming down at the surface down the Chilkat Valley, it forms a cold air dome that sits right over Haines and over Lutak and over the Chilkat River. And that forms a pretty strong convergence zone and strong overrunning as well. And this is exactly what was happening today, where we had north winds. I think the next slide, oh, wait, maybe I'll talk about that later. Yeah, we'll go into that later. So this next slide has a lot of data on it because basically I've got my theory here, right? We've got our south-southeast flow regime and its associated microclimates. We've got our southwest flow and its microclimates, and they're very different, right? Similar, but different. So now I want to throw some data in here and try to prove that those microclimates are real because right now it's all conjecture. So if we just look at the top third of this slide, I've grayed out the bottom part, so we're focusing on the top here. During our south-southeast flow regime, which is what we have today, are really snowy events. I wrote the class here as very snowy types of events. I picked out 4 months from the last 21 years that show this type of flow regime really clearly, where we had very consistent flow coming out of the south-southeast. So December 2013 was one of those really snowy months. November 2011 and January 2012 we talked about, and then March 2010 as well. So here's the amount of precipitation at customs and at the airport and in town, and then the amount of snowfall at customs and in town. And the airport doesn't measure snow, so we don't have that data, which is why there's no third column here. So if we look at these south-southeast flow events, that should look like this. Well, it turns out that if you look at the numbers here at the bottom, there's significantly more precipitation that falls in town during these events and significantly more snowfall as well. So in fact, it's 48% drier at customs than in town, 45% drier at the airport than in town, which I thought was really interesting. Even though the airport is so close to town, it's basically as dry as customs. It's basically the entire Chilkat Valley is very dry. And then right when you get to town, you're in that fjord, that's where you get the heavy precipitation during this type of south-southeast flow. And on the average, it's 16% snowier in town during this type of event. Now, if we look at southwest flow, this second kind of flow regime, we have less precipitation at customs. Again, we have less at the airport, but it's actually increasing. We have more of a linear increase as we go up the valley this time, which is a difference for sure. More precip in town, but not as much more. And then the big difference here is that it is way snowier, way more snow falls at customs than in town during these southwest flow events. In fact, 75% more snow falls at customs during a southwest flow event, even though it's 31% drier at customs than in town. And then I put a third category in here that's meant to represent the kind of the average of the two different flow regimes. So I'm calling this alternating flow patterns. And this is a more typical storm that we have here, where it starts as snow in Haines, and then it turns to a south wind, and it turns to rain, and it warms up. And a lot of the time it'll keep snowing out the highway when that happens, right? So these alternating flow patterns, the storm may start out looking like this with south-southeast flow, and then it transitions through the event, the flow backs to the south, and then it backs to the southwest, and it turns into a southwest flow event. So that kind of alternating flow pattern, paradigm, or regime has its own microclimate systems, and they're interesting. One of the things of interest is that the airport gets way less precipitation during this class of storm. And the city of Haines does get more, and there's more snow at customs. So it's kind of an average of the two, southwest and southeast flow, with the exception that the airport is extremely dry, which is surprising when you look at the data, but not surprising if you've ever driven up the highway and seen how dry it is out there. 61% drier at the airport during these alternating flow events. So I guess the question now is, does that data match this model that I've built? Where with south-southeast flow, it should be 48% drier at customs. Yeah, I'd say that matches. 45% drier at the airport, more or less. Snowier in town, well, that's evidenced by the convergence zone. So that's consistent with the theory. Now let's look at the southwest flow events, where we said it was 31% drier at customs. Okay, 19% drier at the airport, definitely, and 75% snowier at customs. Well, that is evidenced by this convergence zone that sets up the highway. So that one makes sense as well. It's not perfect, but I think the model generally works. If you have a southwest flow storm, that you're going to have microclimate a lot like this. And conversely, if you have a southeast flow storm, your microclimates are going to tend to look like this. And it seems to work pretty well in my experience here in Haines. So those are the two main flow regimes, but I also want to bring up two special cases. One of them happened today for a couple of hours, and the other happened last week for a couple of hours. So this first special case here is a southerly flow or a south flow, where the 850 millibar, the mountaintop level flow, is blowing out of the south, and it's angled just right that it's driving a south wind through Lynn Canal and a southeast wind going up the Chilkat Valley. So it's warm and melting out the snow in this Chilkat Valley. But when the flow is lined up just right out of the south, we can maintain a north wind out of Skagway and an east wind out of the Kotzebue Valley. And what this does is it injects cold Arctic air into Lutak and into town. And so you end up with a convergence zone that it really only exists on the north side of town. So if you were to go down to the Pyramid Island beach, like Cars Cove, Chilkat River, or anywhere south of there, you're going to be on the warm side here where it's raining and above freezing. But if you go to the north side of town, like let's say from Mountain Market north up towards Young Road and then around to Lutak, you'll be in heavy snow. And that did happen today. We did have a warm south wind that was blowing up the Chilkat River for a couple hours today, and it did turn into a southeast wind at the airport and go a little bit up the valley. I'm not sure how far up the valley it made it. And we had cold wind, north wind coming out of Skagway during that time. So this did happen today. And this can lead to surprises when, let's say, the Weather Service is expecting it to rain in town because they're expecting a southerly wind to come up Lynn Canal, and it does happen. But if the flow is just right and we still have a north wind coming out of Skagway, we'll often stay as snow in town and end up with a lot more snow than expected, at least in the town site, and definitely Lutak. So here's the picture of that happening today. So we had a south wind coming up the fjord. We had an east wind at the airport. It warmed up to 32 degrees at the airport. And during that same time, we still had at the Haines Boat Harbor, there was still a north wind, 29 degrees blowing out of Skagway. So we had this convergence zone set up right over town. Even when the winds were backing and shifting a little bit, that convergence zone maintained where it was, and it just continued to dump snow really hard today. And that's what it looked like here at the library. It was snowing about as hard as it ever does. It was really amazing. When you're under that convergence zone, it can be severe sometimes. And the last flow regime I'm going to talk about, this special case here of west-northwest flow, which doesn't happen quite as often. It basically can only happen when you have a low pressure system that was to the south, and then it jumps over the mountains and it's moving up into the Yukon rapidly. And what that does is it sucks the south wind up the fjord behind it, and it tends to suck a cold Arctic west-northwest wind out of the Chilkat Valley. And that leads to another kind of oddly shaped convergent zone that is more on the Chilkat side and in the Lutax side. But if you're on this east side of the fjord where the warm south wind is blowing up, then you'll be out of that convergent zone and you'll be in rain, whereas there'll be heavy snow happening over here. So that's another complexity that happens from time to time, but not as often as the main flow regimes. Okay, so that's my main talk about microclimates. But I do want to spend a couple more minutes talking about December 2020, because this was such an interesting weather event for a number of reasons. As you guys know, it broke all the records. It didn't just break the records, it shattered the records. It was inches additional rain on top of the previous rainiest event for a 24-hour period, for a 48-hour period, for a 10-day or a 7-day period. It really blew the records out of the water. And one of the other strange things about that event was that it rained so much more in Haines than it did in Skagway. And it rained so much more in Haines than it did in Juneau, which is odd. It usually rains more in Juneau. And even Gustavus, you know, places on the other side of the mountain range that should have gotten more rain during that event than us, we got way more rain during that event. So it kind of makes me wonder, you know, does that 2020 atmospheric river, does that event fit our theorized model of microclimates that I just presented? So I dug up as much data as I could. There's very little data of really existing, but we have rain totals from the airport. There's a personal weather gauge on Mount Riley Road, and then there's another personal rain gauge on Letnikoff. So I pulled the precipitation data from those three gauges for December 1st and December 2nd. That's the main event of that. Sorry, that should say 2020, not 2021. My mistake. But this was, no doubt about it, this was a strong southwest flow event. It looked just like the other atmospheric rivers, except it had a little bit more moisture associated. So, you know, I would have expected the microclimates for that event to look like this, right? We should have been drier in town and at the airport than down on the peninsula. There should have been more rain to the south, a little bit less in town and a lot less up the highway, and then snow at the border. But if we look at this rain gauge data, there's something really interesting here. If you look at December 2nd, it rained 5.49 inches at the airport, and on Mount Riley Road, 5.50, almost the exact same amount of rain in town as at the airport. And then if we look at December 2nd, 4.77 inches, and then Mount Riley Road, 4.81, again, almost the exact same amount of precipitation for both days. And if you look at the 2-day total, it's pretty much identical. It rained exactly the same amount in town on the top of Mount Riley Road as it did at the airport, which is kind of shocking for me. I've never seen a storm here that it has rained as much at the airport as it has out here in the fjord. But even more shocking to me is if you look at these rain totals from Letnikoff. It actually rained significantly less on both days down at Letnikoff. And I have another anecdotal report from across the bay at Mud Bay that confirms this, that it actually did rain significantly less out there than it did in town. And again, that really goes against everything I know about our microclimates here. I've never really seen a storm that has done this and rained so hard at the airport and in town and much less elsewhere, including Skagway and Juneau and Gustavus. It was snowier at Customs. They did have a dome of cold air that was stuck in the valley, and there was a lot more snow up there. There was also a lot of rain. But yeah, this was a hard thing for me to explain when I looked at this data. Yeah, so it should have looked like this, and instead it looked more like this really localized pocket of very heavy rain. And that's about it. So, you know, I've been trying to figure out reasons as to why this may have happened like this. And I have a couple of ideas. There's a phenomenon called lee side convergence that can happen on the lee side of a mountain where the flow comes around to the right of the mountain, it comes around to the left of the mountain, and as it gets to the other side, it wraps around and that flow converges on the lee side, and you can get heavy rain from that in some cases. So maybe something like that was happening over town. But also, I mentioned hydraulic jumps earlier in the presentation. Is it possible that there was some kind of atmospheric hydraulic jump that was happening over the Chilkat Range? So if we go back to this diagram, we have our strong southwest flow coming up over the mountains. If that's the Chilkat Range, the flow is descending down the lee side, and it's possible that there was a jump here. And normally when a hydraulic jump happens, this air is very dry on the lee side, so you don't get much precipitation here. You just get a little cap cloud or a little lenticular cloud that can happen. But if you have a situation like we do, where we're in a fjord and there's a lot of warm, moist southerly flow coming up the fjord at the surface, down here, what you basically have, you're injecting a bunch of moisture into this part of the mountain. And so if a hydraulic jump did form here, you can see how there'd be enough moisture and a huge amount of lift to create heavy precipitation. And it turns out that this is a phenomenon that has been studied a couple of times around the world. It's not very well understood because there's not very much data that shows this kind of stuff happening. But here's one example. This is a paper from 2012. It's an island called Jeju Island in South Korea. And some atmospheric scientists went down there with 2 Doppler radars, and they put a Doppler radar on one side of the island and a Doppler radar on the other side of the island. This black line here is the shape of the mountain. And with their dual Doppler radars, they were able to image a typhoon as it came through, and the winds were blowing strong with a lot of tropical moisture from right to left in this image. They were able to image the amount of lift in the atmosphere and the amount of precipitation. So what this image is showing is that as the wind is blowing up over this mountain, you get a huge amount of lift and a lot of precipitation on the windward side here. And then you get this blue is showing subsiding air. So the air is coming back down this side of the mountain. But somewhat unexpectedly, they found a very strong, narrow band of heavy precipitation that happened just outside the lee slope of the mountain. And from their data, they were pretty convinced that this was a hydraulic jump feature, and that because this is an isolated island where the flow was able to move around both sides of the island and then reconverge on the backside where you had lee side convergence and a bunch of moisture being brought around the island, then that gets injected into the hydraulic jump and you get heavy precipitation. And sure enough, what these guys found was that during this typhoon event, this was the maximum amount of precipitation on the whole island. More rain fell right here than on these steep slopes of the mountain, which is very unexpected. So there might be something to the hydraulic jump theory. You need very particular conditions for that to happen. Was that happening here in Haines in December 1st, 2020? I don't know for a fact, but I have a hard time explaining how that much rain fell over such a localized area and did not fall in other areas nearby. So maybe something like this was going on. And as a little bit of evidence of how this kind of stuff could happen here, this is an image that I took last winter. This is looking southeast down the Chilkat Valley this is Chilkat Lake under the fog here. And there's Mount Riley right there. So town is right up here. So we're looking towards town down the Chilkat Valley, and this is the Chilkat Range is right over here. And what you're seeing in these cloud patterns, this is a mountain wave event. So the flow is coming up over the Chilkat Range, or it's rippling from the Fairweather Range even, and it creates these waves just like the wave in the river. And at the crest of each wave is where these wave clouds form. So there's a wave there, there's a wave crest here, there's a trough in here, and then another crest of a wave here. So, just the fact that you can see these waves undulating in the atmosphere above the Haines town site, it does make me think that something like a hydraulic jump could happen. The geography might be just right for a wave to happen, or for a hydraulic jump to happen. So that's the bulk of the talk in terms of microclimates. I'm just going to show you guys a couple of quick things just to put them on your radar in case you've never seen them. The first is the Haines Precipitation Tracker website, which we built at the Haines Avalanche Center as a service for Haines. So you guys can go to this website and you can monitor the storms as they come in. And one of the things that we've added at the bottom, this is relatively new, is a microclimate comparison tool. So at the bottom here, you're going to see a bar graph of the rain totals, current rain totals at the airport, out at Lutak, town, that's the top of Mount Riley Road, and at Letnikoff. And so this airport gauge, that's the official FAA rain gauge at the airport. That's a heated rain gauge. So if it snows, it's going to melt that snow and count that as rain. Whereas these three gauges are actually personal weather stations that people have been very kind to put that data online so that we can access it and we can all benefit from it. But these rain gauges are not heated. So if there's snow involved, they're going to under-report the precipitation that's falling. So I just want to show you that really quick. This is the Haines precipitation tracker. It'll show you current warnings from the Weather Service, the amount of precipitation at the airport over the last couple of days, and then you can compare it here to the December 2020 record event and the November 25 event, and you can compare 2005 to 2020 because I think it's really interesting to compare those two. We also have a plot here. This is showing you the current temperature at different elevations. So here's 0 feet, 1,500 feet, 3,000 feet, 4,500 feet. And up at 4,500 feet at mountaintop level, it's 18 degrees. Down here in the valley, it's 27. And up in the middle, it's 30 Fahrenheit. It's also going to show you the snow level. And it's going to show you the snow water equivalent, which is an indication of how much snowpack there is. That means there's 39 inches of water equivalent that still needs to melt out of the snowpack this spring and this summer. So here's more SWE, snow water equivalent data. There's a chart of precip. Here is the forecast precipitation from the National Weather Service over the next 48 hours. And then there's that microclimate comparison. So I encourage you guys to go to this website, bookmark it, and anytime a storm comes in, you should check it out. It's pretty fun to watch in real time. And the reason there's no rain gauge data showing for Lutak Town and Letnikoff is because this storm happened to be all snow. So when that snow melts, these gauges will start going up. Okay, I told Margaret Plucker that I would end this presentation on a positive note and promise everybody that spring is coming, the snow is going to melt, and that warmer, sunnier times are ahead. And it's not even a lie, it's true. I think there's an indication that next week we might have a pattern change and hopefully some warmer weather coming. So on that note, thank you guys for bearing with me through this complicated presentation. And here's some resources that I encourage you guys to all check out for the curious. And I would love to answer some questions. I'll look at the chat box now. I've been ignoring it this whole time.
All right. Thank you very much, Erik. That was very, very interesting. It's nice to see some observations, driving up and down the highway like I do almost every day of maybe some theories as to what's going on. Yeah, let's get some questions. You can use the raise hand feature if you'd like. That makes it easy. If you can't find it, just shout out. I think that works out okay too. Russ White has a question in the chat. How much December 2nd rain fell at Lutak versus town?
Great question, Russ. I wish I knew the answer to that. There is no rain gauge that I know of out at Lutak, or there wasn't. And since that event happened, I did talk to some residents out there, and they were gracious enough to buy a weather station themselves and put that data online. So we now have at least personal weather station data out at Lutak that we did not have back in December. So going forward, I hope to be able to answer questions like that. Any guess? I really can't say. The Lutak microclimate is one that I've had a hard time figuring out myself. I used to house sit out there, and I spent a fair bit of time living out there. But I found it very hard to predict whether it was going to be more or less precipitation in Lutak compared to town. And if anyone else has any insight on that, I'd love to hear it.
Patty Brown has a question in the chat. What are the exact locations of the Lutak and Mount Riley weather equipment? I'm especially interested in altitude.
Yeah, and so one of the ways you can figure that out, so you can look at the Haines precip tracker, and that actually doesn't tell you the elevation. But if you go to weatherunderground.com, that's where I'm pulling the data from. So if you go to wunderground.com and you look at the Haines area, they have a map of the local gauges in the Haines area. And you can click on the gauges and you can learn all about them, what kind of weather station and what altitude and where on the map. The LUTAC station is on the LUTAC Spur Road, just across the bridge, and it's at 0 feet, or like 5 feet maybe. And the Mount Riley Road station is at pretty near the end of Mount Riley Road, pretty much the top of the sledding hill, I believe.
And another one from Larry Charles Stevens.
Oh, that's my dad.
Oh.
Hey, Dad. Let's see. It was another rain event approaching. The magnitude of the 2020 event. Oh, if were another rain event approaching the characteristics and magnitude of the 2020 event, are you in a position to apply your models to predict it? Good question. I think this event shows that with these really strong atmospheric rivers, they behave in a way that's a little different than we're used to seeing here in Haines. So, from a forecasting perspective, from my perspective, I might think, hey, watch out down on Mud Bay. It's going to be a lot of rain down there. And it was a lot of rain down there, but it ended up, that would be the wrong advice because it ended up raining more at the airport, which I would have never guessed. So I guess the answer is no. I think we need more studies in this area to try to answer that question. And I think we need more rain gauges and more weather stations. And that's one of the things that the Avalanche Center has been working for years to try to get more weather stations in Haines. And I'm optimistic that with all of the new attention on landslides here, that we will have more weather stations installed in the future to help us understand these events better.
Erik, do we ever get Chinook winds here? I can't say that I've ever really felt like I experienced one, at least not like you'd get down in the Rockies, But it seems like we should at times.
You know what? That's a really good question. And it's not very common here, but it does happen. Skagway in particular gets, it's called a Foehn wind or a Chinook wind, or in Juneau they call it the Taku wind. It's the same phenomenon. And it's basically a very strong, warm, downsloping wind. And in our region, it happens when you have a strong easterly flow that comes out of the interior, out of British Columbia, and it comes over the top of the Coast Range and it descends down into the fjord. And when the conditions are just right and the stability is just right and the flow direction is just right, that downsloping Chinook Foehn wind that can hit the Haines Harbor. And I remember a day, I think it was last January, something like that, that the winds were gusting 80, 90 miles an hour at the boat harbor. But then you'd get to the other side of town and there was nothing quite that severe happening. And that was that exact phenomenon. There was a downsloping Chinook wind. So yes, but not very often.
Any more questions?
Looks like Patty Brown has a question here in the chat. Would it be useful to have a LUTAC road weather station on the east-facing slope? It might be quite different from the station at the Chilkoot River mouth. The liquefaction of the moraine was such a huge surprise. Yes, I totally agree. I think one of the things that I would like to advocate for over the coming years is for a automated weather station that would be somewhere in the mountains, not too high up, maybe at 1,000 feet or 1,500 feet, but higher up than the valley bottom and on that east slope to the east of Mount Rapinski and 3920 above the LUTAC area. And that's kind of the source watershed of a lot of the water that's flowing downhill into the LUTAC area. So yeah, I think that would be a very, very prime location for a professional automated weather station.
Do you think there's is there a big effect from the ice fields and the glaciers here on affecting airflows and cooling the air temperature? And do you think as we see all the glaciers sort of march back and up and over the ridges that we'd be able to measure that in the near term, or is that far off in the distance?
Well, they measure that kind of stuff near Anchorage. They measure it near Fairbanks in the Alaska range. All it would really take is a research team that was interested in answering that question. Professional weather equipment's a little bit expensive, but there are cheap ways to do it. And we do have a lot of those glacier effects. And that's one of the things we didn't have time to talk about tonight was the wind patterns that come off of glaciers. Most of our valleys that have a glacier at the top are going to have cold, downsloping glacial winds blowing at night and then turning to an upslope wind in the afternoon usually. And that does a lot to affect the temperature and the cloud patterns as well.
Yeah, I've just in the last 15 years or just under 15 years, I've noticed a difference in some of those upper valleys like the Jarvis and Glacier Creek, that in the summer, it's a lot warmer there than it used to be. And in the evenings, especially, with those really cold winds just don't happen as often. And I would think that surely that's going to impact the plants and all kinds of other things there in those valleys.
Yeah, it's a strong driver of climate for sure. I know the heli skiers talk a lot about glacier effect and valley effect because when they're looking for slopes that are safe or trying to look out for slopes that might be a little less safe, they're paying pretty strong attention to what the winds are doing. And that glacier effect is a big driver of how the snow falls. It's a big driver of the temperatures in the area. And it's important.
Russ White asked how much it costs to set up a weather station.
Well, if the budget was there and I had the money to set up a dream weather station, like a standard professional weather station, the budget's usually going to be $20,000 to $30,000 for a remote automated weather station. But there are ways to do it cheaper. And so that Haines Avalanche Center, we put up a station, as Russ knows. I think he helped us carry some stuff up there on Mount Rapinski. And the budget for that project was a lot less. I think we did it for somewhere around $5,000 or $6,000 total. And we had a lot of equipment that was donated from other Avalanche centers, so that helped. But that was bare bones. That station's just barely scraping by, and it needs a lot of work. It needs money put into it for sure.
Anyone else have a question? All right. Well, Patty Brown says thank you. Thank you from me and from the Tokshnuk Watershed Council. It was a very informative, very interesting talk. We could probably do 2 more on the same topic, but maybe in the future. Next week, we're going to try to talk about hooligan and history and cultural significance. Same time, Thursday at 7, with Meredith Pokart and Ted Hart and maybe some other folks. So please join us for that. And this recording will go up on the Tokshnuk website as soon as possible, and I'll post it on Facebook also. I think that's it. Unless you've got anything else to say, Erik?
No, that's it. Thank you, everybody. Thanks, Derek. Thanks, Tokshnuk.
Yeah, thank you all, and have a nice snowy April evening.